Hello there. Welcome to this first video from a short series of videos based on Cellular Automata and the game of life. I am assuming you already know what Cellular Automata are, so I'm not going to explain them in depth. I'm just going to provide you a little quick overview about them. But in case you are not familiar with them, you can go to this website. It's on Wolfram, and here you can read about the history, why they're so interesting, and why they're important for computing. In essence, cellular automata are systems that are built on a grid, and this grid can have different cells, and each cell can have two states. It's either dead or alive, and we represent those states with two numbers, 0 or 1, 0 for dead and 1 for alive. So the algorithm consists on checking what is going to be the state of some cell based on the state of its neighbors, and we check the previous state to know what the current state will be. So that's in a nutshell how that works. So let's see the principles within TouchDesigner. Let's begin with a table. In this first video we're going to be implementing a one-dimensional version of a cellular automata, and it's going to be a simplified version of a 1D system, because later on we're going to create a complete version from the intuitions we gain doing this exercise with a simplified version. So in this simplified version, we are going to be checking only the neighbors from the current cell and not include the cell itself. So I'm going to be checking, if I'm this cell, I'm going to be checking my neighbor on the left and my neighbor on the right to determine if I'm going to be alive on the next state. So like we saw, we define if a cell is alive or dead with a number, 0 for dead, 1 for alive. So in this situation where we check left and right, we have a number of possible states, and those are here. So these are only 4. And why this? Well, because it could be that my left neighbor is dead and my right neighbor is alive. So that's state number 1. It could be that my left neighbor is alive and my right neighbor is dead. That's state number 2. It could be that both of them are dead. That's state number 3. Or it could be also that both of them are alive. That's state number 4. I don't have any more possibilities. Alright, so based on those 4 possible states, I can create a set of arbitrary rules. So what do I mean by that? I mean that, for example, in the first state, where my left is dead and my right is alive, in the next step, I will be alive. I could choose to be alive, for example. That will be my rule for this first situation. For the second one, I could choose that I'm dead. For the third one, I'm alive. For the fourth one, I'm dead again. And this is quite arbitrary. So we could decide that the rules for this are like that. The first case, I'm dead. The second, I'm alive. In this, I'm dead, and the next one, I'm alive. But if you do these rules in order, so if you start from the most basic set, so 0, 0, 0, 0, where I am totally dead, and you keep doing this, so your first rule will be 0 for all the states. Your second rule will be 0 for all states except for the last one. Your third rule will be 0 for the 2 first, and 1 for the third, and 0 for the last one. Then you start to notice a pattern, and this looks suspiciously binary, right? Because in fact these are the binary numbers. So 0, 0, 0, 0 is 0, 0, 0, 0, 1 is 1, 0, 0, 1, 0 is 2, and so on. So as we can see, if you keep doing this by hand, and I encourage you to do this in a piece of paper and just keep writing all the binary numbers until you reach the last number, you will see that there's 16 possible numbers. And yeah, even though writing it by hand in a paper is a good exercise to understand this, I also get it if you don't want to do that. You can simply use a Python script, like this one, to output from a decimal number a binary number. So let's fill this table with all the numbers from 0 to 15, and we get these 16 numbers. These are all the possible rules I have with these 4 possible states. And remember this is the simplified version I have chosen, because the complete version has many more possible rules. But for the sake of simplicity, let's deal with this. So now, how are we going to do this? The way we're going to do it is by using a pixel shader. So don't be scared about that, about shading programming. This is a good opportunity perhaps to dive into that if you have been waiting to do so, because it touches very fundamental aspects of a shader. It's also not super hard to do, it's actually very simple, so it's gonna be quite fun to do it, I hope. So let's dive into our pixel shader. Okay, to begin, let's create a base. This base, we're gonna call it CA1D, Cellular Automata 1D, and we're gonna go inside, create a GLSL. My GLSL is going to be our grid. So quickly, let's conceptualize this. First of all, let's make this grid a little bit smaller, so 64 by 64. We're gonna represent a one-dimensional Cellular Automata system in this two-dimensional space. So how does that work? Basically, we're going to stack each state in time of the one-dimensional system in the y-axis of this texture. So the first row will be state in time 0, the second row state in time 1, and so on. So that is why we use this 2D texture. But keep in mind, we're still doing a one-dimensional cellular automata. It's not a two-dimensional one. We're just simply using the second dimension to visualize this in time. That's all. All right. So let's begin writing our code. To do that, let's invoke the code editor. And here, we're going to begin by creating a structure that defines our cell. So struct cell, this is where we're going to store the information for each individual pixel. So now I'm not going to call them pixels, I'm just going to call them cells, to be clear, okay? So what we need to store in cell is first the position of the cell in the grid, and second its state, if it's alive or dead. So this can be 0 or 1, as you know, and that is the definition of my cell. So let's begin by creating a cell. So I'm going to declare here my cell C, and I'm going to initialize its values, position to something, and its alive state to 0 to begin with. The position has to be, of course, the location of the pixel in the space of the grid. And I could use here the normalized version of it, so accessing it with VUVST, but I'm not going to use that because that's normalized and it's a little bit harder to conceptualize. It's easier for us to work with integer coordinates, so we're gonna be looking one step to the left and one step to the right, and that is easier to think about if we used simply the resolution and the coordinates of the grid as they are. So I'm gonna use here an i-vec2 xy, which is gonna be an i-vec2 of the GLFrag coord.xy. This is the real coordinate number from the whole grid, and this is in integers. That's why I want to use it, because it's easier to conceptualize in this example. All right, here we have it. We have created a cell, we have the position and a live state. The next thing we want to do is we want to pass the alive state of this cell to the texture. So let's put it in the RGB colors. We only need one, but let's put it in all of them so we can see it. And there we go. So this has turned black clearly because all of the cells are at the beginning dead. So that is good for us. Now, what else do we need? In any system with cellular automata, we need to have a seed. So we need to initialize the system with some seed. What does that mean? It means that one of the cells has to be alive, at least one, otherwise they will remain dead. So which one? The classic thing to do is to choose the center one. And since we are doing here a 1D system, remember we're dealing first with the first row. So we need to check if my position, so the position of the cell, is equal to 0 or minus or equal to 0 to do something there. So here I'm gonna initialize the seed, right? Now I set the middle one from the first row. So this is my first row. How do I get the middle one from there? So I think the easiest way to do it will be to make it alive if the C position of the cell is equal to the resolution divided by half, right? So that's alive, and if not, it's dead. We need to declare the resolution, so let's declare it here. Back to res, we can use the put info, this variable declared by TouchDesigner for us, to the output info, I think it's correct, and this should be fine. And now we see one of them is alive. Yes, the middle one. Nice. So this, so far so good. And if it is not the first row, then it's any other row, and that is later in time, right? We said the first row is T0, T1, T2, T3, so now we're in T0. And if it's not T0, then only then we do our calculations. So here we do our calculations. Perfect. So now, what are our calculations? Our calculations are, like you remember, to check our neighbors, the left and right neighbors. So to do that, let's create a new function here. Let's just call this check neighbors. Neighbors, I always write this wrong. Neighbors, I'm sorry, English speakers. I never remember how to do this word neighbors. And here we're going to pass an in-out cell C, because yeah, it's just more comfortable. We don't want to return anything. We just want to write directly to the cell if it's alive or dead. And in here we need to do a couple of things. The first thing is we clearly need to sample the neighbors. To sample the neighbors, I could use the texture function, but the texture function does interpolations and I just want the right value. So I'm gonna use texelFetch instead. So texelFetch, I'm gonna sample from somewhere. So I'm gonna use the std2d inputs. I'm gonna use my data, and I'm gonna define data to be the input 0 of my shader. Okay, so that will go there. Then from where do I sample? So let's create here the neighbors. So first of all, my neighbor on the left, L, is gonna be equal to, clearly on the left is -1, but now on the Y, think carefully for a second, what should be on the Y? Remember that we're stacking the one-dimensional systems vertically. So if I am in the second row, so that means T1, I need to look to T0. Where is T0? 1 down. Tuck. So for every row I need to look 1 down. So that means this has to be -1. And then for vec2 R, we need the same but to the right. There we go. And now texelFetch is going to return the dead or alive value or my neighbor cell on the left and on the right. And that is just an integer, right? So that integer is going to be the state for the left. It's going to be a cell. And in here we're going to pass the coordinate. That is going to be the current cell, the cell position, current cell position that comes from these inputs, plus the left for the state on the left. Let's just call this state left so it's more clear. Position, and then and this has to be an ivec2 for texelFetch, and texelFetch requires a third argument for the level of detail, which we don't need, and we only need the red channel because remember this goes through RGB, so we could sample either one of those, but we just choose now to do R, and we set this an int, so then cast this to an int. Then we have some error, and that is because, yeah, we're asking std2d inputs, and we don't have any inputs coming to the shader. So now let's think about this for a second. What do we want this data input to be? What is the data input? So the data input is the grid itself, because we want to check the previous states of the grid. So we need to pass itself back in time. How do we do that? Well, let's first create an output here, out. And if you ever played with feedback, you may realize that feedback is just a delay of 1 frame, which is exactly what we need. We need to see the time -1 for the next state. So let's put here a feedback. That's going to give us the previous state. We connect the feedback to the first input. Is that the first input? Yes. Good. Let's just leave it like this. And we fed feedback the grid here. Perfect. And feedback doesn't like not to have anything connected, so we just connect whatever. Doesn't really matter. So let's just put a constant here. And let's just make it black so it doesn't bother our eyes. All right. And that's all. Next, we proceed with the code. Now we see that it's doing this feedback thing. Now we need to sample the right. So state left, and let's sample now the right. And for the right, we need to add here R, not left. And for convenience, I'm going to combine these two in a new vector called neighbors that is going to contain the alive and dead states for both of them. So alive states for neighbors. I wrote it right. That's good. Nice. And I think that's so far so good. So here we sample the neighbors. That's great. Then we need to create the rules or sample the rules. The rules, if you remember, are all those binary rules that we created here. So this long list of values. And for this particular example, I don't want to declare an array of arrays because that is a little bit verbose in GLSL, so I'm gonna just do it with a single array. We have 16 rules, so we have all these, and each one of the rules contains 4 values. So we need an array as big as 16 times 4, and we need to say 16 times 4, and here we're going to declare all these rules. And now we simply can copy them from the values we generated. Let's just do this like that. And now we have all my rules, or all our rules, defined in a single array. And now what we need to do is to create some mechanism to read this in the correct way. So let's think about it for a second. To access all the values for rule 0, we need the indices 0, 1, 2, and 3. For rule 1, we need the indices 4, 5, 6, and 7. So how do we accomplish that? So one way will be to create, for example, a location that is going to be based on some rule that we're going to pass, rule times 4. Because if I say that my rule int rule is equal to 0, 0 times 4 is 0, so I'm here. To sample the next one, I will do that plus 1, the next one plus 2, the next one plus 3. If I want rule 1, which is this one here, then I will do 1 times 4 is 4. So 0, 1, 2, 3, 4. I'm here. 4, 4 plus 1, 4 plus 2, 4 plus 3. So that's why we do this. So let's here create indeed the int rule array, because we need all those 4 values. So I'm going to declare here a new array of 4 integer values. And this is going to be my rules with the location, what I just said, offsetted with a 1, 2, and 3. So 1, 2, and 3. And that should be it. So loc plus 1, plus 2, and plus 3. So this lets us index this in the right way, even though it's just one array. Alright, so let's save. That looks good. Once we sample the rules, next thing to do is to make the comparisons. So compare with the states. So now, if you remember, the states were this that we saw here. Possible states. We have 4. 0, 1, 1, 0, 0, 0, 1, 1. So both dead, both alive, left alive, or right alive. We need to check all those states to see the current state of the cell. So let's here create a series of if statements. So if the neighbors are equal to this, to the situation where the left one is alive and the right one is dead, then we want to grab from the rule array, we want to grab 0. The value is going to be equal to 0. So else if the neighbors, the left one is dead and the right one is alive, then the rule is going to be the rule number 1 from my set of rules. Then the neighbors are equal to both alive. Then we do the next one, so that will be 2. And finally, the neighbors are equal to vec2 both dead. Then v is going to be equal to the third one. Okay, so I have now sampled each one of these per rule. That's what we're doing, comparing the states. Finally, we need to assign this to our alive state for my incoming cell. My alive state is going to be equal to this v. And this v has not been declared yet, so let's declare v as 0 to start with. And if we save this, this should yield no errors. Good. So here we are passing the state after the rule comparison. Perfect. And I think we're pretty much done with that. We just need to pass this. Oops, use check neighbors here. And we're going to pass our cell C. And if we do that, we should see some patterns emerging. So let's save it. And nothing comes, maybe because of the rule. So let's try rule 1. Something is going on there. Aha! Some interesting pattern. With rule 2, everything disappears. With rule, whoops, I dropped my stuff. With rule 3, that one is interesting. So as you can see, these rules give you some interesting results already, but wouldn't it be nice to have them as a uniform? I think so. So let's do here a uniform. Sorry. Okay, uniform int rule. Let's call it urule. And let's pass this rule via my function here. Rule. And let's declare here in the function a rule set. So it's I know what, actually can just do this. So let's just declare here rule. Pop up. And there we go. Now we have this defined here, and we just need to, I think we're done with the code, so we just need to pass here a urule, and our rule is gonna be whatever we pass here, so 3 or something. That was nice. One last thing I don't like is that we see that feedback still interpolates, so let's not do that. Let's nearest neighbor, and GLSL should also do that. Okay, great. To finalize this component, maybe we can create here a new control, and here we're gonna call it rule, and for this rule we're gonna pass the parent. Great. So now you can see the rules on this top layer. So that is how you can implement the one-dimensional cellular automata using a pixel shader. And I hope you like this. You're not intimidated by it because it's relatively easy to do and to understand, I hope. And in the next video, we're going to see how to go a little bit further with this. Thank you and stay tuned.